So today's lecture is all about countable subadditivity of outer measure, and it is theorem 3. So let us see the statement: for any sequence of set ei, the outer measure of the union is less than equal to outer measure of the sum of the outer measure of the sets. So this is all about the countable subadditivity formula of outer measure. So let us see, so here we are having some collection of sets. So if we take the outer measure, that is length of the interval, and sum up, we'll get this much length. So instead, if we take union of these sets, we'll get this much length. So obviously, the lower one is less than the above one. The above is the sum of the outer measure of the set, and the lower one is the outer measure of the union. All right, so that is the above one represent the sum of the outer measure, and the lower one represent the outer measure of the union. Okay, so from the picture also it is very clear that outer measure of the union is less than equal to sum of the outer measure of the set. So that is all about the today's theorem. Let us see, for each I, and for each positive number epsilon, there exists a sequence of intervals iij. J is running from 1 to 2, 3, 4 up to infinity, such that ei is the subset. Ei is a subset of the union j running from 1 to infinity iij, and outer measure ei is greater than or equal to summation j running from 1 to infinity length of the interval iij minus epsilon to the power I. This is coming directly from the definition of the outer measure. So yeah, this is coming directly from the definition of the outer measure. This one, for this small number, we'll be able to find a cover of ei. That cover is this is the cover, such that outer measure ei is greater than or equal to summation j running from 1 to infinity length of the interval iij minus epsilon by 2 to the power I. Okay, this is for each I. If you take I is equal to 1, you will get here I is equal to 1, but j is running from 1 to infinity. Alright, if you take I is equal to 10, so I will be 10 here, then still j is running from 1 to infinity in this case also. All right, so this is coming from the definition directly, and this equation inequality is for each I. All right, so yeah, that is all about definition of outer measure. So then if you take union ei, I running from 1 to infinity, that will be a subset of union I running from 1 to infinity, union j running from 1 to infinity. So here double union. So each ei is a subset of union this one, but if you take union ei, so there will be double union here. So and then it shows that cover iij is a cover of this union of ei, because this union of ei is a subset of I running from 1 to infinity, j running from 1 to infinity. So this iij cover, the double index I and j, so is a cover of union I running from 1 to infinity ei. Alright, so from the definition we have outer measure of this set will be less than or equal to sum of the length of the intervals. That is all about writing here, but this much length, after simplification you can write like this using the definition. Okay, using the definition. So yeah, this summation, let us try to simplify this summation. How you simplify? So summation ij running from 1 to infinity length of the interval iij, that is equal to so this is double summation I running from 1 to infinity, j running from 1 to infinity length of the interval iij. So this term, this is less than this one, plus this one. So if you take summation here, summation will be here. All right, so that is equal to this one, but if you take summation this one, that is a geometric series, you will get epsilon. So after all, you get this one. That is what we are writing here, this term. So this one, okay, double summation, and then it is equal to summation I running from 1 to infinity, outer measure of ei plus epsilon. All right, so this is true for any arbitrary epsilon. So therefore what you get, this will be less than or equal to this one. That is what we are writing here. Outer measure of the union of the set will be less than or equal to sum of the outer measure of the sets. Okay, so yeah, that is a very important theorem in measure theory. We have just shown that one. Next is an important example. So this example, so that for any set A and any positive number epsilon, there is an open set O containing O A and such that this one. So for every set A and for every positive real number epsilon, we should be able to find an open set O containing this set A such that outer measure of O is less than or equal to outer measure of A plus epsilon. So this is also very important example. So let us see. From the definition again, for each epsilon we can find a covariance in of A by intervals such that this is true. This is coming directly from the definition of outer measure. So next, so let the interval be denoted by an bn. Okay, the interval in, that is here. So the interval in here, this in, how does it look like, this in? So this in is in this form: close on the left, that is an, open on the right, that is bn. So for each natural number, then in prime, you define in prime like this: an minus epsilon by 2 to the power n plus 1 comma bn. Now in prime is an open interval and in prime is a superset of in. All right, so therefore A will be subset of the union n going from 1 to infinity in prime, and this is union of open interval. Therefore the resulting set O will be an open set. Okay, so obviously A is a subset of this open set. All right, so then just prove theorem that by countable subadditivity theorem, we have outer measure O is less than or equal to summation n going from 1 to infinity length of the open interval in prime, and that is exactly equal to n going from 1 to infinity length of the interval in plus epsilon by 2 to the power n plus 1. But this summation is going to be a geometric series. The sum of that geometric series is epsilon by 2. We're writing here. So it is summation n going from 1 to infinity L in plus epsilon by 2. That is less than or equal to, from the definition, this one is less than or equal to m star A plus epsilon by 2. So if you add up another epsilon by 2, you'll get m star A plus epsilon. Okay, so that is outer measure of O is less than or equal to m star A plus epsilon. That is what we wanted to prove. All right, so example number 3, let us see another example, and this is also one of the important example. So that if m star A is equal to 0, that is outer measure of a set is equal to 0, then outer measure of A union B is equal to outer measure of B for any set B. Okay, if outer measure of a set A is equal to 0, then m star A union B is equal to m star B for any set B. All right, this is also one of the fundamental example. Let us see. So we know that B is a subset of A union B. This is very obvious. B is a subset of A union B. So by countably subadditivity formula, m star B will be less than or equal to m star A union B, and that is less than or equal to m star A plus m star B. That is, I'm here using here the countable subadditivity formula here in this step. Okay, so but m star A is equal to 0, this is exactly equal to m star B. All right, So this number is in between this number and this number, therefore they must be equal, all of them must be equal. So therefore m star b is equal to m star a union b for any set b. So for any set b, this is true. Okay, this is very short example, but one of the fundamental example also. So that every countable set has measure 0. All right, so this is also one of the very important example. So every countable set has measure 0, but we know that every singleton set has measure 0. So every countable set can be expressed as a countable union of singleton set. That is all about the method of the proof. Let A be a countable set, then it can be enumerated as follows. So A can be written as union of the singleton set. So like this. So by countable subadditivity of outer measure, we can write like this: m star A is less than equal to summation n going from 1 to infinity m star xn. So but measure of each singleton set is equal to 0, that is their summation is also 0. M star A is less than equal to 0, but outer measure can never be a negative quantity, so it should be 0. M star A is equal to 0. All right. So now outer measure of different intervals. What I am talking about here, just let us try to see here. So what I am talking about, when we define outer measure of a set A, when we define outer measure of set A, we talk about the collection of cover. So collection of cover, In is a cover of A. That means A is a subset of union going from 1 to infinity In. So then we take the infimum like that. So outer measure of a set A is defined equal to infimum over the collection of cover C summation I is running from 1 to infinity. So length of interval II. So that is all about the definition. And then so this interval you can write II also, In also, doesn't matter. So this interval, I have already told you how does it look like. Interval means interval is equal to AN BN, that is closed on the left side, open on the right side. So we are considering this interval only. How about if you consider interval like this? If the interval In is equal to open interval, if the interval is this open interval, not this interval, then you will have another definition. Let us denote it by m star O of A will be equal to infimum of over the collection CO, let us call it CO, summation I is running from 1 to infinity, LII. It will be like this, where this interval is of this form, open interval. Okay, so the collection consists of covers, and the cover consists of interval, and the interval is open interval like this. So if the definition changes in this form, you will get another outer measure. So what is the relationship between the outer measure originally defined and then outer measure in the new setup, in the new form, in the new cover, in the new interval? So what is the relationship? Are they equal or are they not equal? Okay, the answer is they are equal. All right, so that is all about the next theorem, and that is very important. Like that, you can talk about interval, closed interval also. So you have collection of closed interval, and their union is a superset of A, that is we call it cover by closed interval. So then you think about the collection of such cover, then you think about the infimum of the summation of the length of the interval, and the infimum is taken over all cover. Then you will get another definition of outer measure, and then is that outer measure is equal to the outer measure we have already defined. Then we are going to find out the relationship between these two measures. So many other force. So for every type of interval, we will have a definition of outer measure. All right. So that is all about this theorem. So let us see. So suppose that in the definition of octave measure, let's coming back to the definition of octave measure, M star E, we define infimum over the collection C of cover, a length IN. The collection C of cover, the cover consists of interval. The interval is closed on the left and open on the right. So for set, that is all about. We stipulate number one, IN open set, instead of close on the left and then open on the right, we stipulate IN to be an open interval, and then so IN is equal to AN BN, that is the original definition. Number two, the original definition. Number three, IN is equal to open on the left, close on the right. Number four, IN to be close. Or number five, mixture are allowed. Mixture means interval, any sort of open also can be included, close also, half close, half open, they are all admissible. Okay, so if in this if the definition is defined in this scenario, you will get different octave measure. So what is the relationship of the different octave measure? The answer is they are all equal. Okay, so that is the question. This is a very important one. So that the question is so that the same M star is obtained. Okay, so let us see. We denote the octave measures of the different cases by M star O. This is open interval, octave measure generated by open intervals, and this one, the original one we have been talking about, and this one open on the left, close on the right, and this one a closed interval, and M star M is the mix-up, means it can consist of open also, close also, and then half close, half open, all type of interval is allowed here. Okay, so that means we shall prove that octave measure E generated by open interval is exactly equal to octave measure E, that is the original one, exactly equal to octave measure generated by open close interval, octave measure generated by close interval, and octave measure generated by a mixed interval, that is consists of open interval, close interval, half close, half open, all sort of interval is allowed in this mixed set. Okay, so we shall show that in this case the octave measure is equal to M star ME. M star ME, in this case octave measure is exactly equal to M star ME. Then it is done. Okay, so let us see. Let E be any subset of R. Alright, we denote by C naught, COC, CM the collection of all covers by open intervals. This is collection of all cover by open interval. This is collection of cover by interval, close open interval, that is the original definition, and this one is open close intervals. Okay, and this one is close intervals. All right, and the last one is the mixed interval respectively. Okay, so you think about E, then E will have a cover by open interval, and the collection of all those cover is denoted by C naught, like this. Okay, so CM, it is the collection of all cover by mixed interval. So if you think about the collection of cover by open interval, that will be also member of here, because it is mixed, so it can include this type of collection also, because it is collection of all interval. All right, collection of all cover by all interval, all sort of interval, mixed interval. This is open interval, so this is a superset of this one, a super collection of this one. And like that also, the close open interval also, that is also a cover, collection of cover. That collection of cover is a sub collection of this collection of cover. All right, so similarly open close interval collection, okay, collection of cover by interval of open close, that will be also a sub collection of this one. All right, then a close interval also. So this is very big collection, you know. So each collection is a sub collection of this one. So this is a very big collection. So from big collection, if you take infimum, that will be less than this one also, less than this one also, less than this one also. All right, I have already explained you, if you have a big collection, from that you take infimum, that will be lesser than the sub collection, infimum taken from the sub collection. All right, so infimum taken from the sub collection will be less than the infimum taken from the big super collection. All right, so that is, I have already explained. Infimum taken over this big super collection will be less than or equal to infimum taken from this sub collection CO. So similarly, this one will be less than this one. All right, similarly this one will be less than this one. So lastly, this one will be less than this one. This is obvious, I have already explained you in the previous lecture. So next, from the definition, again we have this one, m star me will be less than equal to m star OE. So this is very obvious. This inequality we have, the reverse inequality we are trying to find out. So for each epsilon, there exists an interval or cover in that is a member of the collection CM, such that m star me will be greater than or equal to summation n going from 1 to infinity length of the interval minus epsilon. This is coming from the infimum definition, and I have already explained this one also. So then we can put in prime, you know, we can put in prime. So what is in prime? It will be in an open interval. All right, how we do this one, let us see how we do this one. So this is, suppose this is any interval an and then bn, any sort of interval, this will be closed, this may be open like that. So you know, if you subtract something from here, say delta, if you subtract delta, then a minus delta will be here, an minus delta will be here, then you can make it open interval like this. Okay, open interval like this. So you have a new open interval, that is in prime, you know, you have a new open interval in prime. This is the original interval. So by adjusting delta, you know, you can make it open, and then in prime will be a superset of in prime will be a superset of, you know, in here. So this is in prime will be superset of in. So that is all about. And then the length of the interval, you know, in is equal to 1 plus epsilon times the length of in prime. All right, or suppose length of the in prime is equal to 1 plus epsilon length of the in, like this one. So you can make this delta so that this length is a multiple of 1 plus epsilon times this one. Okay, so that is all about. You can adjust this one. So from the original interval, you can construct an open interval in prime that is a superset of the original interval. And what is the relationship between the length of the interval? So the original length of the new interval is equal to 1 plus epsilon times length of the original interval. So you can do that one. So yes, you can do that one. Length of the new interval is exactly equal to 1 plus epsilon length of the all interval, original interval. So like that. Now m star me plus epsilon will be greater than or equal to summation n going from 1 to infinity length of the interval, but this length of the interval is exactly equal to this one. If you divide by 1 plus epsilon, you will get 1 plus epsilon inverse summation n going from 1 to infinity length in prime, and that this is greater than or equal to m star OE. Okay, so this is the result. From the above we get this one, 1 plus epsilon m star me plus epsilon 1 plus epsilon will be greater than this one for every arbitrary epsilon. So this is very small number. So what do you get? So ultimately what you get, therefore we have m star m e will be greater than or equal to m star OE. It follows that m star me is exactly equals to m star OE. So the outer measure derived from the open interval is exactly equal to outer measure derived from mixed interval. Okay, so the first result we are able to prove it. So next, case number 2, from the definition we have again, so this will be less than this one also, the original definition. Alright, so for each epsilon there exists in Cm such that, this is coming from the definition of infimum, m star me will be greater than or equal to summation n going from 1 to infinity length of the interval minus epsilon. So again here we can construct and a close open interval in prime with the close open intervals containing in such that length of the new interval is exactly equal to 1 plus epsilon times length of the original interval. So now in prime is a member of the collection C. This cover is a member of this collection of cover. Alright, so now we have this inequality m star me plus epsilon will be greater than or equal to summation n going from 1 to infinity length of the interval is exactly equal to 1 plus epsilon inverse summation n going from 1 to infinity length of the interval in prime will be greater than or equal to 1 plus epsilon inverse m star e. So from above we get this inequality. So from here again, therefore we have m star me will be greater than or equal to m star e. So it follows that m star me is exactly equals to m star eo. Okay, case number 3. So from the definition we have again m star m e is less than or equal to m star oc, open close interval, m star generated by or defined by open close interval. Alright, so for each epsilon there exists an cover in that is a member of the Cm such that m star me will be greater than or equal to summation n going from 1 to infinity length of the interval minus epsilon. Let in prime be the open close interval containing in. So you can define another interval, open close interval containing this one, and you make the length of the new interval such that that is exactly equal to 1 plus epsilon times length of the whole interval. So now in prime is a member, cover in prime is a member of COC. So therefore m star me plus epsilon will be greater than summation n going from 1 to infinity length of the interval. That is, we have done so many times here, this one. So from the above we get this one again, and then therefore we have this one, m star me will be greater than or equal to m star oc. So it follows that again the equality holds true. So case number 4, from the above definition, okay, from the definition we have m star e will be less than or equal to m star ce. Alright, so for each epsilon there exists cover in Cm such that m star me will be greater than equal to summation n going from 1 to infinity length of the interval minus epsilon. Here also we can find out a new interval in prime, and it is a closed interval, and you can make it a bigger one containing in, and also length of the new interval is exactly equal to 1 plus epsilon times length of the whole interval. So if you want to find out length of the whole interval, so you can get it by dividing this interval by 1 plus epsilon. So now this interval cover is a member of the CC. So and this one m star me plus epsilon will be greater than this one. You get this inequality. As usual, you will get this inequality for each epsilon, and then you have this inequality. So it follows that this is exactly equal to this one. Alright, so